Hi, my name is Tammy Miller. In this carboxyl derivatives video, we're going to draw the mechanism of an esterification reaction. To draw the mechanism for an esterification reaction, we need to understand how esters are synthesized. Esters are synthesized by combining a carboxylic acid or a carboxylic acid derivative with an alcohol or an alk oxide. So we've got oxygens that are acting as the nucleophile. There are two ways that we can synthesize these esters. The first is called a Fischer esterification. And a Fischer esterification is catalyzed by an acid. And this is a synthesis of an ester from a carboxylic acid and an alcohol. Esters can also be synthesized by a more reactive carboxylic acid derivative, such as an anhydride or an acyl halide. Lactones or cyclic esters are readily formed using the Fischer esterification of hydroxy acids. So because it's a Fischer esterification, again, this is going to be acid catalyzed. Let's look at a couple of mechanisms. We're going to draw the mechanism for the following reaction. First, I notice that I have a carboxylic acid, and that's going to be attacked by an alcohol. Next, I notice that this is acid catalyzed because they give me this proton and tell me that that is the catalyst. So let's take a look at what this reaction is going to look like. In our first step, the oxygen on the carboxylic acid, the carbonyl oxygen, is going to come and it's going to grab that proton that is the acid catalyst. This will create a carbonyl oxygen that is positively charged. This will actually make the carbonyl carbon more reactive. So now when our alcohol comes in, the oxygen from the alcohol can come and attack this carbonyl carbon. We still have our carbonyl oxygen, which is positively charged because it has 3 bonds. It doesn't like to be positively charged, so it's going to move that bond up here, giving us this molecule. Now, once we have this molecule, we now notice that the oxygen from the alcohol is positively charged. Again, oxygens don't like to be positively charged, so this oxygen is going to kick off that hydrogen. And when that happens, we have the extra hydrogen. Now, anytime we have a nucleophilic attack on a carbonyl carbon, we always have to ask ourselves, can we reform the carbonyl? And here we will be able to reform the carbonyl. And this is because we are going to be able to make a good leaving group. The hydroxyl right here is going to come and it is going to grab that hydrogen that was just released into the solution. This is going to give us a water molecule. Water molecules are good leaving groups. So this is going to go ahead and leave this molecule. Once the water molecule has left, then our oxygen can bring this bond back down and reform that double bond. Once it reforms that double bond, we notice that the carbonyl oxygen is again positively charged. Because it doesn't like to be positively charged, it is going to kick off that hydrogen that is there. And at the end, what we notice is we have reformed this hydrogen that was originally the catalyst. This is how we know that this really is acid catalyzed, because we're reforming that hydrogen. And at the end of this Fischer esterification, we end up with an ester. Let's try a second one. Again, when we look at this, we have a carboxylic acid. and our carboxylic acid is forming a lactone, okay, that cyclic ester. And this again is acid catalyzed, and I can tell this is acid catalyzed right here by the proton that it tells me is a catalyst. So let's take a look at our mechanism. The first step of this mechanism, again, that carbonyl oxygen, just like with the last one, is going to come in and it's going to grab that acid catalyst. What this does is this makes a positively charged carbonyl oxygen, and it makes the carbonyl carbon more likely to react. And here, what's going to happen is the alcohol on the end of this molecule is going to reach around, and it's going to be the nucleophile that attacks that carbonyl carbon. When this happens, the bond from the carbonyl will move up, so I end up with a single bond. I now have this cyclic molecule, and in this cyclic molecule, I see that the oxygen that's in the ring is positively charged. Doesn't like to be positively charged, so what it's going to do is it's going to kick off that proton. Now that I have this proton, I need to ask myself, can I reform the carbonyl? I can if I have a good leaving group. And just like in the last example, the hydroxyl is going to come and it's going to grab on to that hydrogen that has just been released. This is going to give me a water molecule, which is a great leaving group. So this water molecule is going to leave in this step, and we're going to reform that double bond, that carbonyl bond. I now have my carbonyl bond, and my water has left. My carbonyl oxygen, again, is positively charged, which it really doesn't like. So it's, again, going to kick off that proton. In the final piece here, I notice that that orange proton, that acid catalyst, has now been reformed, which tells me this really was a catalyst. So here I've taken a carboxylic acid and I've made a lactone with an acid catalyst. Understanding how to draw mechanisms for esterification is going to be a very common reaction that we see with carboxylic acids and carboxylic acid derivatives, so we need to practice with these.